around 1. And I'm going to look at two different kinds of robust statistics, the trimmed mean and the Windsorized mean. With the trimmed mean, you take a certain percentage of the data from the top and the bottom, you just throw it away and you compute the mean for the rest. With the Windsorized, you take those and then you move those scores into the highest non-outlying score. Now, the 0% is exactly the same as the regular mean, and here it's 1.24. But as we trim off 5% or move in 5%, you can see that the mean shifts a little bit. Then 10%, it comes in a little bit more to 25%. Now we're throwing away 50% of the data, 25% on the top, 25% on the bottom. And we get a mean here of 1.03, that's a trimmed mean, and a Windsorized of 1.07. When we throw away 50%, when we trim 50%, that actually means that we're leaving just the median. Only the middle score is left. Then we get 1.01. What's interesting is how close we get to that even when we have 50% of the data left. And so that's an interesting example of how you can use robust statistics to explore data even when you have things like strong skewness. Next is the principle of resampling. And that's like pulling marbles repeatedly out of a jar, counting the colors, putting them back in and trying again. That's an empirical estimate of sampling variability. So sometimes you get 20% red marble, sometimes you get 30, sometimes you get 22, and so on. There are several versions of this. They go by the names the jackknife and the bootstrap and the permutation. And the basic principle of resampling is also key to the process of cross-validation. I'll have more to say about validation later. And then finally, there's transforming variables. Here's our caterpillars in the process of transforming into butterflies. But the idea here is you take a sort of difficult data set and then you do what's called a smooth function. There's no jumps in it, and something that preserves the order and it allows you to work on the full data set. So you can fix skewed data, and in a scatter plot, you might have a curved line. You can fix that. And probably the best way to look at this is with something called Tukey's ladder of powers. I mentioned before John Tukey, the father of exploratory data analysis. He talked a lot about transformations. This is his ladder starting at the bottom with the -1 over x squared up to the top with his x cubed. And here's how it works. This distribution over here is a symmetrical, normally distributed variable. And as you start to move in one direction and you apply the transformation, you take the square root, you see how it moves the distribution over to one end. Then the logarithm, and you get to the end, you get this -1 over the square of the score. And that pushes it way, way, way over. If you go the other direction, for instance, you square the scores, it pushes it down in the one direction, you cube it, and then you see how it can move it around in ways that allow you to, you can actually undo the skewness to get back to a more centrally distributed distribution. And so these are some of the approaches that you can use in the numerical exploration of data. In sum, let's say this. Statistical or numerical exploration allows you to get multiple perspectives on your data. It also allows you to check the stability, see how it works with outliers and skewness and mixed distributions and so on. And perhaps most importantly, it sets the stage for the statistical modeling of your data. As a final step of statistics and exploring data, I'm going to talk about something that's not usually considered exploring, but is basic descriptive statistics. I like to think of it this way. You've got some data and you are trying to tell a story. More specifically, you're trying to tell your data's story. And with descriptive statistics, you can think of it as trying to use a little data to stand in for a lot of data, using a few numbers to stand in for a large collection of numbers. And this is consistent with the advice that we get from good old Henry David Thoreau, who told us, simplify, simplify. If you can tell your story with more carefully chosen and more informative data, go for it. So there's a few different procedures for doing this. Number one, you want to describe the center of your distribution of data. That's if you're going to pick a single number, use that. Two, if you can give a second number, give something about the spread or the dispersion or the variability. And three, it's also nice to be able to describe the shape of the distribution. Let me say more about each of these in turn. First, let's talk about center. We have the center of our rings here. Now, there are a few very common measures of center or location or central tendency of a distribution. There's the mode, and there's the median, and there's the mean. Now, there are many, many others, but those are the ones that are going to get you most of the way. Let's talk about the mode first. Now, I'm going to create a little data set here on a scale from 1 to 11, and I'm going to put individual scores. There is a 1 and another 1 and another 1 and another 1. Then we have a 2, 2. Then we have a score way over at 9 and another score over at 11. So we have 8 scores, and this is the distribution. This is actually a histogram of the data set. The mode is the most commonly occurring score or the most frequent score. Well, if you look at how tall each of these go, we've got more 1s than anything else. And so 1 is the mode because it occurs 4 times and nothing else comes close to that. The median is a little different. The median is looking for the score that is at the center if you split it into 2 equal groups. We have 8 scores, so we want to get one group of 4, that's down here. And then the other group of 4 is this really big one because it ranges way out. And the median is going to be the place on the number line that splits those into 2 groups. That's going to be right here at 1.5. Now the mean's a little more complicated, even though people understand means in general. It's the first one we have here that actually has a formula where m for the mean is equal to the sum of x, that's our scores on the variable, divided by n, the number of scores. You can also write it out with Greek notation if you want, like this, where that's sigma, a capital sigma is the summation sign, sum of x divided by n. And with our little data set, that works out to this: 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 9 plus 11. Add those all up and divide by 8, because that's how many scores there are. Well, that reduces to 28 divided by 8, which is equal to 3.5. If you go back to our little chart here, the 3.5 is right over here. You'll notice there aren't any scores really exactly right there. That's because the mean tends to get very distorted by outliers. It follows the extreme scores. But a really nice, I say it's more than just a visual analogy, is that if this number line were a seesaw, then the mean is exactly where the balance point or the fulcrum would be for these to be equal. People understand that. If somebody weighs more, they got to sit in closer to balance somebody who weighs less, who has to sit further out. And that's how the mean works. Now, let me give a little bit of the pros and cons of each of these. For the mode's really easy to do. You just count how common it is. On the other hand, it may not be close to what appears to be the center of the data. The median, it splits the data into 2 same-size groups, the same number of scores in each. And that's pretty easy to deal with, but unfortunately, it's hard to use that information in many statistics after that. And then finally, the mean. Of these 3, it's the least intuitive, it's the most effective by outliers and skewness, and that may really strike against it, but it is, however, the most useful statistically, and so it's the one that gets used the most often. Next, there's the issue of spread your tail feathers. And we have a few measures here that are very common also. There's the range, there are percentiles and interquartile range, and there's the variance and the standard deviation. I'll talk about each of those. First, the range. The range is simply the maximum score minus the minimum score. And in our case, that's just 11 minus 1, which is equal to 10. So we have a range of 10. And I can show you that here on our chart. It's just that line there at the bottom from the 11 down to the 1. That's a range of 10. The interquartile range, which actually is usually referred to simply as the IQR, is the distance between Q3, which is the 3rd quartile score, and Q1, which is the 1st quartile score. If you're not familiar with quartiles, it's the same as the 75th percentile score and the 25th percentile score. Really what it is you're going to throw away some of the data. So let's go to our distribution here. First thing we're going to do is we're going to throw away the 2 highest scores. There they are. They're grayed out now. And then we're going to throw away 2 of the lowest scores. They're out there. And then we're going to get the range for the remaining ones. Now, this is complicated by the fact that I've got this big gap in between 2 and 9. And different methods of calculating quartiles do something with that gap. So if you use a spreadsheet, it's actually going to do an interpolation process, and it'll give you a value of 3.75, I believe, and then down to 1 for the first quartile. So not so intuitive with this graph, but that is how it works usually. If you want to write it out, you can do it like this. The interquartile range is equal to Q3 minus Q1. And in our particular case, that's 3.75 minus 1. And that, of course, is equal to just 2.75. And there you have it. Now, our final measure of spread or variability or dispersion is 2 related measures, the variance and the standard deviation. these are a little harder to explain and a little harder to show. But the variance, which is at least the easiest formula, is this. The variance is equal to, that's the sum, the capital sigma is the sum of x minus m. That's how far each individual score is from the mean. And then you take that deviation there and you square it, you add up all the deviations, and then you divide by the number. So the variance is the average squared deviation from the mean. I'll try to show you that graphically. So here's our data set, and there's our mean right there at 3.5. Let's go to one of these 2's. We got a deviation there of 1.5. And if we make a square that's 1.5 points on each side, well, there it is. We can do a similar square for the other score at 2. If we're going down to 1, then it's going to be 2.5 squared, and it's going to be that much bigger. And we can draw one of these squares for each of our 8 points. The squares for the scores at 9 and 11 are going to be huge and go off the page, so I'm not going to show them. But once you have all those squares, you add up the area and you get the variance. So this is the formula for the variance. But now let me show the standard deviation, which is also a very common measure, is closely related to this. Specifically, it's just the square root of the variance. Now, there's a catch here. The formulas for the variance and the standard deviation are slightly different for populations and samples in that they use different denominators. But they give similar answers, not identical, but similar if the sample is reasonably large, say over 30 or 50, then it's going to be really just a negligible difference. So let's do a little pro and con of these three things. First, the range. It's very easy to do. It only uses two numbers, the high and the low, but it's determined entirely by those two numbers. And if they're outliers, you've got really a bad situation. The interquartile range, or IQR, it's really good for skewed data, and that's because it ignores extremes on either end. So that's nice. And the variance and the standard deviation, while they are the least intuitive and they are the most affected by outliers, they are also generally the most useful because they feed into so many other procedures that are used in data science. Finally, let's talk a little bit about the shape of a distribution. You can have symmetrical or skewed distributions, unimodal, uniform, or U-shaped. You can have outliers. There's a lot of variations. Let me show you a few of them. First off is a symmetrical distribution. Pretty easy. They're the same on the left and on the right. And this little pyramid shape is an example of a symmetrical distribution. There are also skewed distributions where most of the scores are on one end and then they taper off. This right here is a positively skewed distribution where most of the scores are at the low end and the outliers are on the high end. This is unimodal. It's our same pyramid shape. Unimodal means it has one mode, or really kind of one hump in the data. That's contrasted, for instance, to bimodal, where you have two modes. And that usually happens when you have two distributions that got mixed together. There's also uniform distributions where every response is equally common. There's U-shaped distributions where people tend to pile up at one end or the other and a big dip in the middle. And so there's a lot of different variations, and you want to get the shape of the distribution to help you understand and put the numerical summaries like the mean and like the standard deviation and put those into context. In sum, we can say this. When you use descriptive statistics, that allows you to be concise with your data, tell the story and tell it succinctly. You want to focus on things like the center of the data, the spread of the data, the shape of the data. And above all, watch out for anomalies because they can exercise really undue influence on your interpretations. But this will help you better understand your data and prepare you for the steps that follow. The next step in our discussion of statistics and inference is hypothesis testing, a very common procedure in some fields of research. I like to think of it as put your money where your mouth is and test your theory. Here's the Wright brothers out testing their plane. Now, the basic idea behind hypothesis testing is this. You start with a question, and it's something like, what is the probability of X occurring by chance if randomness or meaningless sampling variation is the only explanation? Well, the response is this. If the probability of that data arising by chance when nothing's happening is low, then you reject randomness as a likely explanation. Okay, there's a few things I can say about this. Number one, it's really common in scientific research. Say, for instance, in the social sciences, it's used all the time. Number two, this kind of approach can be really helpful in medical diagnostics where you're trying to make a yes-no decision. Does a person have a particular disease? And three, really, anytime you're trying to make a go, no-go decision, which might be made, for instance, with a purchasing decision for a school district or implementing a particular law, you base it on the data and you have to make a yes-no. Hypothesis testing might be helpful in those situations. Now, you have to have hypotheses to do hypothesis testing. You start with H sub 0, which is the shorthand version for the null hypothesis. And what that is in and what that is in lengthier terms is that there is no systematic effect between groups. There's no association between variables, and random sampling error is the only explanation for any observed differences that you see. And then contrast that with H sub A, which is the alternative hypothesis. And this really just says that there's a systematic effect, that there is in fact a correlation between variables, that there is in fact a difference between two groups, that this variable does in fact predict the other one. Let's take a look at the simplest version of this, statistically speaking. Now, what I have here is a null distribution. This is a bell curve. It's actually the standard normal distribution, which shows z-scores and relative frequency. And what you do with this is you mark off what are called regions of rejection. And so I've actually shaded off the highest 2.5% of the distribution and the lowest 2.5%. What's funny about this is even though I draw it to plus and minus 3 and it looks like it hits 0, it's actually infinite and asymptotic. But that's the highest and lowest 2.5%. Collectively, that leaves 95% in the middle. Now, the idea is then you gather your data, you calculate a score for your data, and you see where it falls in this distribution. And I like to think of that as you have to go down one path or the other. You have to make a decision. And you have to decide whether to retain your null hypothesis, maybe it is random, or reject it and decide, no, I don't think it's random. The trick is things can go wrong. You can get a false positive. And this is when the sample shows some kind of statistical effect, but it's really randomness. And so, for instance, this scatter plot I have right here, you can see a little downhill association here, but this is in fact drawn from data that has a true correlation of 0. And I just kind of randomly sampled from it until I got this. It took about 20 rounds, but it looks negative, but there's really nothing happening. The trick about false positives is that's conditional on rejecting the null. The only way you can get a false positive is if you actually conclude that there's a positive result. It goes by the highly descriptive name of a type 1 error, but you get to pick a value for it, and 0.05 or a 5% risk if you reject the null hypothesis. That's the most common value. Then there's a false negative. This is when the data looks random, but in fact it is systematic or there's a relationship. So for instance, this scatter plot, it looks like it's pretty much a 0 relationship, but in fact, this came from two variables that were correlated at 0.25. That's a pretty strong association. Again, I randomly sampled from the data until I got a set that happened to look pretty flat. And a false negative is conditional on not rejecting the null. You can only get a false negative if you get a negative. You say there's nothing there. It's also called a type 2 error. And this is a value that you have to calculate based on several elements of your testing framework. So it's something to be thoughtful of. Now, I do have to mention one thing, big security notice, but wait. The problem with hypothesis testing, there's a few. Number one, it's really easy to misinterpret it. A lot of people say, well, if you get a statistically significant result, it means that it's something big and meaningful. And that's not true because it's confounded with sample size and a lot of other things that just don't really matter. Also, a lot of people take exception with the assumption of a null effect or even a nil effect, that there's 0 difference at all. And that could be, in certain situations, it could be an absurd claim. So got to watch out for that. There's also bias from the use of a cutoff. Anytime you have a cutoff, you're going to have problems where you have cases that would have been just slightly higher, slightly lower. It would have switched on the dichotomous outcome. So that is a problem. And then a lot of people say that it just answers the wrong question because of what it's telling you is, what's the probability of getting this data at random? Well, that's not what most people care about. They want it the other way, which is why I mentioned previously Bayes' theorem, and I'll say more about that later. That being said, hypothesis testing is still very deeply ingrained, very useful in a lot of questions, and it's gotten us really far in a lot of domains. So in sum, let me say this. Hypothesis testing is very common for yes-no outcomes. and it's the default in many fields. And I'd argue that it is still useful and informative despite many of the well-substantiated critiques. We'll continue in statistics and inference by discussing estimation. Now, as opposed to hypothesis testing, estimation is designed to actually give you a number, give you a value, not just a yes, no, go, no go, but give you an estimate for a parameter that you're trying to get. I like to think of it as sort of a new angle, looking at something from a different way. The most common approach to this is confidence intervals. Now, the important thing to remember is this is still an inferential procedure. You're still using sample data and trying to make conclusions about a larger group or population. The difference here is instead of coming up with a yes, no, you instead focus on likely values for the population value. Most versions of estimation are closely related to hypothesis testing, sometimes seen as the flip side of the coin, and we'll see how that works in later videos. Now, I like to think of this as an ability to estimate any sample statistic, and there's a few different versions. We have parametric versions of estimation and bootstrap versions. That's why I got the boots here. And that's where you just kind of randomly sample from the data in an effort to get an idea of the variability. You can also have what are called central versus non-central confidence intervals in estimation, but we're not going to deal with those. Now, there are three general steps to this. First, you need to choose a confidence level, anywhere from, say, well, you can't have 0. It has to be more than 0, and it can't be 100%. Choose something in between. 95% is the most common. And what it does is it gives you a range of numbers, a high and a low. And the higher your level of confidence, the more confident you want to be, the wider the range is going to be between your high and your low estimates. Now, there's a fundamental trade-off in what's happening here, and it's the trade-off between accuracy, which means you're on target, or more specifically, that your interval contains the true population value. And the idea is that leads you to the correct inference. There's a trade-off between accuracy and what's called precision in this context. And precision means a narrow interval, and it's a small range of likely values. And what's important to emphasize is this is independent of accuracy. You can have one without the other, or neither or both. In fact, let me show you how this works. What I have here is a little hypothetical situation. I've got a variable that goes from maybe 10 to 90, and I've drawn a thick black line at 50. If you think of this in terms of percentages and political polls, it makes a very big difference if you're on the left or the right at 50%. And then I've drawn a dotted vertical line at 55 to say that that's our theoretical true population value. Then what I have here is a distribution that shows possible values based on our sample data. And what you get here is it's not accurate because it's centered on the wrong thing. It's actually centered on 45 as opposed to 55. And it's not precise because it's spread way out from maybe 10 up to almost 80. So this situation, the data is no help really at all. Now here's another one. This is accurate because it's centered on the true value. That's nice, but it's still really spread out. And you see that about 40% of the values are going to be on the other side of 50%. It might lead you to reach the wrong conclusion. So that's a problem. Now here's the nightmare situation. This is when you have a very, very precise estimate, but it's not accurate. It's wrong. And this leads you to a very false sense of security and understanding of what's going on. And you're going to totally blow it all the time. The ideal situation is this. You have an accurate estimate where the distribution of sample values is really close to the true population value and is precise. It's really tightly knit, and you can see that just about 95% of it is on the correct side of 50, and that's good. If you want to see all four of them here at once, we have the precise two on the bottom, the unprecise ones on the top, the accurate ones on the right, the inaccurate ones on the left. And so that's a way of comparing it. But no matter what you do, you have to interpret a confidence interval. Now, the statistically accurate way that has very little interpretation is this. You would say the 95% confidence interval for the mean is 5.8 to 7.2. Okay, so that's just kind of taking the output from your computer and sticking it into sentence form. The colloquial interpretation of this goes like this. There's a 95% chance that the population mean is between 5.8 and 7.2. Well, in most statistical procedures, specifically frequentist as opposed to Bayesian, you can't do that. That implies that the population mean shifts. That's not usually how people see it. Instead, a better interpretation is this: 95% of confidence intervals for randomly selected samples will contain the population mean. Now I can show you this really easily with a little demonstration. This is where I randomly generated data from a population with a mean of 55, and I got 20 different samples. And I got the confidence interval for each sample, and I've charted the high and the low. And the question is, did it include the true population value? And you can see that of these 20, 19 of them included it. Some of them barely made it. If you look at sample number 1 on the far left, barely made it. Sample number 8, it doesn't look like it made it. Sample 20 on the far right, barely made it on the other end. Only one of them missed it completely, that sample number 2, which is shown in red on the left. Now, it's not always just 1 out of 20. I actually had to run the simulation about 8 times because it gave me either 0 or 3 or 1 or 2. And I had to run it until I got exactly what I was looking for here. But this is what you would expect on average. So let's say a few things about this. There are some things that affect the width of a confidence interval. The first is the confidence level, or CL. Higher confidence levels create wider intervals. The more certain you have to be, you're going to give a bigger range to cover your bases. Second, the standard deviation, where larger standard deviations create wider intervals. If the thing that you're studying is inherently really variable, then of course your estimate of the range is going to be more variable as well. And then finally, there's the N, or the sample size. This one goes the other way. Larger sample sizes create narrower intervals. The more observations you have, the more precise and the more reliable things tend to be. I can show you each of these things graphically. Here we have a bunch of confidence intervals where I'm simply changing the confidence level from 0.50 at the left side up through 0.999. And you can see it gets much bigger as we increase. Next one is standard deviations. As the sample standard deviation increases from 1 to 16, you can see that the interval gets a lot bigger. And then we have sample size going from just 2 up to 512. I'm doubling it at each point. And you can see how the interval gets more and more and more precise as we go through. And so let's say this to sum up our discussion of estimation. Confidence intervals, which are the most common version of estimation, focus on the population parameter. And the variation in the data is explicitly included in that estimation. Also, you can argue that they're more informative because not only do they tell you whether the population value is likely, but they give you a sense of the variability of the data itself. And that's one reason that people argue that confidence intervals should nearly always be included in any statistical analysis. As we continue our discussion of statistics and data science, we need to talk about some of the choices that you have to make, some of the trade-offs, and some of the effects that these things have. We'll begin by talking about estimators. That is, different methods for estimating parameters. I like to think of this as what kind of measuring stick or standard are you going to be using? Now, we'll begin with the most common. This is actually called OLS, which is short for ordinary least squares. This is a very common approach. It's used in a lot of statistics, and it's based on what's called the sum of squared errors. And it's characterized by an acronym called BLUE, which stands for Best Linear Unbiased Estimator. Let me show you how that works. Let's take a scatter plot here of an association between two variables. This is actually the speed of a car and the distance to stop from about the 20s, I think. We have a scatter plot here, and we can draw a straight regression line through it. Now, the line that I've used is in fact the best linear unbiased estimate, but the way that you can tell that is by getting what are called the residuals. If you take each data point and draw a perfectly vertical line up or down to the regression line, because the regression line predicts what the value would be for that value on the x-axis, those are the residuals. Each of those individual vertical lines is a residual. You square those and you add them up, and this regression line, the gray angled line here, will have the smallest sum of squared residuals of any possible straight line that you can run through it. Now, another approach is ML, which stands for maximum likelihood. And this is when you choose parameters that make the observed data most likely. It sounds kind of weird, but I can demonstrate it. And it's based on a kind of local search. It doesn't always find the best. I like to think of it like a person here with binoculars looking around them, trying hard to find something, but